In this lecture, we're going to talk about network regularization. We're mainly going to talk about several techniques on a fairly high level. If you would look at the book Deep Learning from Goodfellow et al., you would see that for several of the regularization techniques, there's some theoretical derivation showing you a bit of what these techniques might do in a simplified setting. I'm just not so sure that these simplified derivations are really indicative of what's going on in practice. However, if you're interested in looking at some of these derivations, you're encouraged to check out the book Deep Learning, and there's a chapter on regularization techniques. We're going to review the story of polynomial fitting just as an aspirational thing before we look at regularization. So this is the story you've heard in a basic machine learning class, where the problem was to fit a function to these given blue points, these points that are shown as circles here. And so we would like to find a polynomial. So this is the axis x that goes in this direction, and up here it says t, but let's say this is a function of x. We would like to fit the polynomial f of x that passes through these points, or that at least passes reasonably close by to these points. And if we fit a higher order polynomial that has as many degrees as freedoms as we have points, then we can generally expect this polynomial to be overswinging quite a lot. So you see from the first point, the polynomial would go way up, who knows how high, then come all the way down, and it would maybe for some part, like here, you might think it reasonably approximates the data, but there are some other parts, for example, between these 2 points, it creates this bump that is not really justified, and then it could also go way up or way down, like way outside of this graph. So the techniques to prevent this polynomial to fit so much and to have these crazy oscillations were either to fit the polynomial of a lower degree or to use some regularization, such as the L2 regularization. There are 2 reasons I would like to bring it up. First, just to remind everybody what this regularization is about. And second, also as a warning that this regularization in deep learning behaves differently from this regularization that was used with this illustrative example of polynomial fitting. We might discuss a few of these things later in the class when we talk about training dynamics. And for now, I guess we'll mainly focus on how do these different regularizers work. Let's just start top down. So having a complete neural network, we can have a different regularizer for each layer of the network. Then combining the regularizers for different layers, we can use different weights for the regularizer of each of the layers. But even within a layer, we could conceivably use different weights for the different parameters inside a layer. One typical example would be a linear layer where the bias term might not have any regularizer attached, and the other parameters, other weights, would have a regularizer attached to them. So one way to write that in an equation would be to say we have a regularizer that regularizes the complete network, and we'll have a network with k layers. So we have k is the index, and then this w1 to wk would be the weight tensors for each of the k layers. And so we would sum up from 1 to k a lambda I that is a layer-specific weight times the regularizer used for the layer I. and this regularizer is a function of the parameter tensor of this particular layer. But that already poses some issues. For example, the parameters of a layer might actually not be nicely fitting inside of a tensor. We could think of a convolutional layer. Maybe in our abstraction, a convolutional layer could have filters that have size 3 by 3 and others 7 by 7, and then these two filters could not be combined into a tensor. Also, the bias term might not fit nicely together with the other parameters of a convolution. Further, it's possible to attach multiple regularizers to the same layer. So maybe conceptually, it's best to think of this regularizer design as some sort of a plug-and-play system. You can just pick a layer and maybe a subset of the parameters of the layer and attach a regularizer. And then you just add as many regularizers as you want. You can attach one or multiple regularizers per layer. You can pick what weights to attach the regularizer to, and you can freely select the parameters. Of course, in praxis, you don't want to go that crazy, so it is much more common to have maybe all the linear layers have the same type of regularization with the same regularization strength, and rather than someone really selecting different type and different parameters for every regularizer for every layer. For the next few regularizers, I'll simply use this notation where you want to regularize a set of weights. So this k is the same index as before, but it just means we have a bunch of weights, and these are scalar weights now. And so then we'll sum up over something where I is in an index set. So this just says which of these weights, that means which are the indices of the weights of the parameters that should be regularized. Also, I'm going to omit the parameters lambda I. You just have to add them conceptually just later on. So these regularizers are very simple anyways. Okay, so the first one is L2 regularization, where we have the parameters we want to regularize. And so what we do is we sum up over all the parameters and we square them. If you think of all the weights parameters that you want to regularize arranged in a vector, then this would be the 2 norm squared of that vector. That's where this name L2 regularization comes from. L2 regularization is very popular. You might think of it as some form of default choice. As an additional term to know, L2 regularization is also called weight decay. For some notational convenience, sometimes it makes sense to actually have this regularization parameter lambda multiplied by 1/2, so that this 1/2 cancels out with the square terms that you get when you take the derivative and compute the backpropagation and update the weights. Now, this is a technical detail if you look at some of the derivations, how these regularizers are used. L1 regularization then is you're summing up overall the weights parameters you want to regularize, and you take their absolute value. So again, if you think of all the parameters arranged in a vector, that would be the 1 norm of the vector. The elastic net regularization is a combination of L1 and L2 regularization. It's actually not really necessary to introduce as a separate concept as long as we understand that there's this plug and play idea of regularizers, that you can just add multiple regularizers to the same layers or to the same network parameters. Now here, if you would have it as a separate regularizer, you would need to have these separate parameters lambda to trade off this 1 norm and the 2 norm. Actually, this equation is a bit messed up, so I apologize for that. I guess this lambda 1 should be in here and this lambda shouldn't be here. Okay, what parameters to regularize? So for linear layers, the multiplicative weights, so not the bias terms, these are common. The maybe the weights of convolutional layers is common, and maybe not the bias terms in fully connected and convolutional layers. It generally seems that it doesn't make a lot of sense, but if you leave it in, it's not gonna create a big difference either way. One thing, I leave that for you to look up. Do you actually want to normalize the parameters for, regularize the parameters for batch normalization? So how do we want to set the strength of the individual regularizers? We said that the design choices are quite open, so you could really have lots of different parameters, lambda I. But that's just conceptual. I mean, in practice, you probably want to vary as little as possible. So use maybe the same parameters lambda for all different layers that are somewhat similar. And I think most architectures, these parameterization weights, they change very little. So the Max Norm Constraint ensures that the weights that contribute to one output or one neuron are small or equal to some threshold const. And here, with some of the weights, we mean some LP norm, maybe the L1 norm or the L2 norm. So for each output, for example, in a linear layer, or maybe for each conv filter, we would like to check that the sum of the weights square is small or equal to const square. Or maybe the sum of absolute values is small or equal to some constant. And then if this sum of the weights, or the norm on the weights, exceeds some threshold, then we project onto the ball with radius const. So then we just change all the weights, we shrink all the weights a bit, such that the norm on the weights is exactly the maximum. Dropout is a technique that is very widespread and is something that is important to know because it's referenced very often in the literature. We'll have a parameter that is a probability P. And what we are going to do is, inside the network, we are going to set values to 0 with a probability P. Specifically, we'll have just tensors, traveling through our network. And what we'll do is we'll grab one of these tensors and then we'll visit each scalar inside this tensor, and with probability P, we will set this value to 0. And all the other values that are not set to 0, we will scale by 1 divided by P. That means if the probability P is 1/2, then we will go over each value in this tensor and set it to 0 with probability 1/2. And all the surviving scalars in the tensor, we will multiply with 2. So that means some values in absolute So for some values, they will get smaller or closer to 0, and the other values will move further away from 0. And during inference, we eliminate this dropout layer. Again, let's just write this with some more formal notation. The easiest really to imagine this dropout is as a separate layer in the network that has a tensor that comes as input and one modified tensor that leaves as output. So, and both of these tensors have the same size, and we just say this is some tensor that has number of channels, a width, and a height. But of course, this also applies to vectors or whatever other tensor you would like to think of. So for each output value, and this is the index, so this in each output value indexed by this C, W, and H, we'll start with the corresponding input value, and then we'll flip this coin, so we select some random value between 0 and 1, and check if it's smaller than the probability P. This is the Iverson bracket in this context, so that if this condition evaluates to true, then this is going to be 1. If it's false, it's going to be 0. And then we're going to take this whole thing and we're going to multiply with 1 divided by P. Okay, this actually shouldn't be here. So once this selects 0, then everything evaluates to 0. If this is going to be a 1, then this leading term 1 divided by P will be multiplied with this input value. This is a visualization of dropout for a fully connected network. What you see here is the first layer, maybe the input layer, second layer, third layer, and dropout would do something equivalent to just killing a neuron. So the killed neurons are shown in black here. That means for the surviving neurons, for example, this white circle, it would receive fewer inputs. The technique that I explained is actually called inverted dropout, which is a way to implement dropout. The scaling is necessary that we introduced, but in the beginning, people actually tried to do the scaling during inference time. But that has problems and makes this a lot more unstable, because this gives rise to more mistakes. And also, you would kind of have to remember this parameter that was used to train the dropout. This creates some unnecessary link between training and inference, so that inverted dropout is basically superior in all aspects. All right, so dropout changes the expected value of the output. If we eliminate half of the inputs, loosely speaking, it makes sense without doing any mathematics that we expect the output to shrink by a factor of 1/2. If we eliminate 20% of the inputs, then we would expect the output to shrink by 20%. So to undo this expected reduction or this expected shrinkage of the output, we just multiply it by 1 divided by P. And since P is a value smaller than 1, 1 divided by P is greater than 1, and therefore this correction factor will make all the surviving values weighed by a larger amount. All right, so this regular dropout P, we would just scale the weights by P during inference, and inverted dropout we scale by 1 divided by P during training. So even though it's maybe a small additional cost, still just multiplying by some value p during inference might be an additional cost you don't want to have. Again, think about mobile phones or billions or millions of inference calls. They might be time critical, and also it's just risky. You might mess up the code much easier if this training and inference are linked in a way where you need to kind of remember the parameter you used during training. So here's some code example. We import NumPy here, and as parameter, we select the probability p equals 0.5. My tensor that I will send to the dropout layer is a 3 × 4 matrix. Think of it as some grayscale image. So the code computes a mask that has the same shape as the input, and you just create random values, one for each scalar in this tensor, and then compare it to p. So this first thing gives you a value that is either 0 or 1, or actually maybe true or false, and then you divide by p. So finally, the dropout, this is a component-wise multiplication between the input and the mask. All right, let's run this. So what we see here is some random image that we send to the dropout layer, and then dropout would create a mask that is as big as this input, and then we see, since we use 50% dropout, there will be zeros wherever something is zeroed out, and twos where we are not zeroing it out, because the weights have to grow by a factor of 2 when they survive the dropout. And then this is the final tensor that will be sent forward into the network. So let's just check one of these values. So minus 0.77 becomes minus 1.5. So it is multiplied by 2. Let's just, for entertainment, let's pick 0.9. So here, with a probability of 0.9, we'll keep a lot more of the values. So you see that only a single value here was selected for dropping, and because the probability is a lot higher, a lot less gets dropped. The way these other values grow is only by a factor of 1.11111. So this is a basic technique. I guess it even remains to be the most popular variant, but of course with such a simple techniques, everybody can come up with a super small modification or a larger modification. So you see a very large number of alternative versions, maybe DropConnect, variational dropout, spatial dropout, dropout for RNNs, concrete dropout, curriculum dropout, adversarial dropout, efficient dropout for CNNs, spectral dropout, many papers to look at if you're more interested in this topic. Some other discussion, dropout can be interpreted as adding noise to the data. So in some sense, you add some form of noise, and adding this noise makes the network more robust to noise, and therefore it should generalize better. There is an abstract example that's often given in connection with dropout. That is, if you think of one neuron, one output, that is a weighted combination of several inputs. And we expect, or we picture in our head that these input features would correspond to high-level concepts that are detected in an image. Maybe we want to classify cars, and one of the features is detecting windshield, the other feature is detecting wheels, and another feature is detecting some grill, and another feature is maybe detecting a street. And so what we would like to have is that the network gets robust to maybe the absence of some of these features, and you still want to be able to classify a car, even though not all of these features are present. And so what this dropout might do by dropping some of these features to help you make a decision, it forces you to spread out the weights a bit more, and it forces you to consider multiple features when making a decision. Again, this is some inspirational example. It's not 100% clear if something like this really applies in practice, or if this is really the concept that makes dropout work. Another such inspirational interpretation, again, you have to take it with a grain of salt, is to think of dropout. Actually, one particular configuration of dropout creates something that you could call a subnetwork, or it's a network that's less complex than the original one, but each dropout configuration basically gives you a different type of network. And what dropout does in this interpretation is it trains an ensemble of many different networks at the same time. So next, dropout is typically only applied to certain layers, and the probability P can change per layer. A typical example is to use dropout for later layers in image classification, and not use it much in earlier layers, or not at all. Then dropout was very popular before 2015, but since then we've seen several networks that don't use dropout at all. Also, my personal feeling is that dropout works well for classification networks, where we start with maybe a large tensor, and then the tensor gets smaller and smaller with fewer features, and at the end we only want to have a decision which of many classes the image should be classified as. There are other networks that generate a lot of outputs, such as segmentation networks or depth prediction networks. Now, in these networks, it seems to be more damaging to start dropping out information, because these networks have to predict some information per pixel, and if you start dropping a few information from neighboring pixels later on when you try to predict something, it might be too damaging, or it's just a general observation that for these type of dense regression networks, or networks that create a lot of different just a lot of outputs, this dropout is not popular. Early stopping is a technique that is also often considered as a regularization technique. So the question is when to stop training. One idea is to plot the error on the training set and on the validation set, and you stop training when the error on the validation set starts to increase. The loss or error on the training set generally decreases with more training, and it can in some sense decrease forever or kind of saturate and get stuck. So the error on the training set is not really expected to go up in many deep learning contexts. So the validation set is there to tell you when should you approximately stop training. If you look at some technical derivation in a simplified setting, you will see that early stopping has a similar effect to L2 regularization. Multitask learning is the concept of trying to solve multiple tasks or multiple problems at once. Let's say that maybe below we have a network that tries to predict segmentation and normals and depth for each pixel in an image. So the image would be fed in down here, and then after a while, these are the shared layers, the network would split up into 3 different parts, where the first part is devoted to task A, let's say is segmentation. The second, then this branch here is devoted to task B, let's say the normal prediction. And the third branch is devoted to task C, the depth prediction. And then this is shown as one block. This might be one layer, but this could also be multiple layers that are inside this box here. And the same is true for these other task-specific layers here. What we hope to achieve here is that by extracting features that are useful not only one task, but for multiple tasks, that these kind of shared layers would kind of regularize the network, and it would improve overall performance. So a successful multitask learning would then in the end have better performance on task A and task B and task 3 than if you would train 3 networks separately, one for only task A, one for only task B, and one for only task C. A variation of this you see if, for example, let's say we don't have this task B and C, people might add some side branches to earlier layers in the network to maybe check that there's some meaningful progress in earlier layers. So maybe if the overall task is a classification network, you could still add some minor branch here, and also with the same loss and the same goal, add kind of a mini classification network just to check that the earlier layers are also training well by themselves. This is another regularization technique. This is a general machine learning technique adding noise to network outputs. I'll just show the example label smoothing here. Assume you have one classification problem with one hot encoding of ground truth labels. So maybe the third class is the correct one, so there would be a 0 probability for the other classes and a 1 for the correct class. Maybe training with the cross-entropy laws, we would be concerned that the network, it cannot really generate the 1 and it really cannot generate the zeros, but the network would try to push higher and higher closer to the 1 and lower closer to the 0, and this might be hurtful. So we'll give the network some less ambitious goal, or maybe some smooth goal. Also could be justified with uncertainty. We're just not really so sure what the label is, so let's lower the probability a bit. So we say that there's some uncertainty parameter epsilon, some smoothing parameter epsilon, and then the correct class, we lower the probability from 1 to 1 minus epsilon. And then to compensate for that, all the other probabilities we need to increase from 0 to epsilon divided by k, where k is the number of classes minus 1. So the sum of probabilities would still be 1. Batch normalization in one interpretation can also be considered as a regularizer. During training, using batch normalization, we estimate a mean and a standard deviation, so a mean mu and a standard deviation sigma, only using a few samples within a mini batch. But it's kind of random what other samples is one particular sample grouped with. This creates what we could call some noise. So we could think of this batch normalization during training, that this mu and sigma are some estimate of the true mu and sigma of the whole data set or the whole population under consideration, plus some noise. And this noise is the deviation of the estimation in the mini batch from estimation in the complete population. So this is kind of this injection of noise that could be seen as a regularizer, because again we kind of make the network more robust to noise, hoping that it will generalize better during inference. So this DropConnect I liked for an idea, maybe again not a very popular technique that is used a lot, but I thought it's one of the versions of Dropout that is kind of interesting. So in Dropout, we randomly set tensor values to 0. But then when this tensor is passed on to the next layer, and one value has been set to 0, it will be a 0 input for all values that will use it. So this DropConnect actually doesn't set tensor values to 0, but it actually sets network weights to 0. This results in a better random pattern, as we'll see in the following. So I'll just show a dropout, a simple version first, and then a figure from the paper. So a dropout example for a linear layer that has a parameter tensor parameter matrix W, and it has an input vector x in and an output vector x out. That means x out equals W times x in. This matrix here is just some matrix I picked that would show the W's, and so this matrix here is W, and this is the vector x in. When we, before coming to this linear layer, pass this vector x in to a dropout layer, then some values will be changed to 0, and others will be multiplied by the 1 time divided by p factor. So in my example here, I pick a dropout probability of 0.5. So randomly the second and the fourth value were set to 0, and the other two are multiplied by 2 to compensate. So 2 times 2 is 4, and 2 times 6 is 12. If we rewrite this, then we can say that this second entry here actually multiplies the second column of the matrix, and this fourth one here multiplies the fourth column of the matrix. So alternatively, I could have multiplied the weight matrix itself by a factor 2 and set these columns, the second column and the fourth column, to 0. Looking at that, this is not a very nice sparsity pattern. Just by starting with the matrix and manipulating the matrix weights directly by looking at each scalar value here and then either multiplying by 2 or setting to 0, I would generate a nicer pattern. So this is the figure of the paper, again comparing some of this DropConnect idea. So you would get maybe a if this is now a bigger matrix, you just show the sparsity pattern, it would give like a nicer, more nicely distributed sparsity pattern rather than what you get from Dropout. Now, what we showed in the previous slide is that in my simple example, the dropped columns would correspond to how this looks like for the next layer. But if you actually think of one vector and how the previous layer affects it, then you would get these rows being dropped. Okay, so, but this is a minor detail too. I think it's enough to think about columns of this matrix being dropped. All right. So just some other random idea. You could do something like dropout on complete layers. So during training, you randomly skip some layers, and during testing, you use all layers. So this is some example. Maybe during training, you skip certain layers. Maybe you skip the gray ones and only use the orange ones. And then during testing, during inference time, you use all the layers. Data augmentation will be discussed later, but this is also another technique that can be considered as regularization. All right, I'm gonna leave it here. And I think next we're gonna discuss this data augmentation in more detail.